So maybe that we have a piece of the video that is cut, okay? We will find today at this point 2 videos, first part and second part. Okay. Now it should work. Okay, any questions so far before I start? Let me see, what time is it? It's 2:07. Okay, good. Okay, let me make a premise. Okay, first of all, but this quick. The first link is not something that you have to learn for the exam. And so you can put a cross over it. And the first link, basically, in the web page presents what I just discussed. But there are a couple of more things that I would like to tell you from this web page. And when I told you it's important that you get the big picture, I need to add one more detail. This big picture needs to be updated continuously. So today, this may be lucky or unlucky. We have to continue to study forever. I'm still studying a lot, reading papers, because everything is continuously changing. Changing, I would say, on average for the better. So change is a good thing. And also change is a good thing because change in life, you see nature is continuously changing, because in this way, everything gets more resilient and more flexible. So change is a good thing, but on the other hand, it implies that some adaptation, and adaptation involves also updating your background. And this is well explained in a Wikipedia page presenting what from the social sciences, what are deemed to be the 21st century skills that you find here. Which is interesting. It's an interesting read because there is here, for instance, this table, which shows, in a way, it guides you through the process of learning what are the skills, the general skills, not technical, not very specific, that are deemed to be essential in the modern society, which are divided in 3 categories: learning and innovation, digital literacy, career and life. So first of all, learning and innovation, I think there is no need to comment most of these individual skills. Critical thinking and problem solving. Indeed, employers look for people who solve problems, not for people who create problems. And this is, I mean, something trivial to say, but keep it in your mind, because really, if you think among the persons that you know, how much we appreciate people who solve the problem. And there are people who, for their attitude, they create problems in a way that when you make a proposal, like, let's do this, let's make this research plan, this research proposal, there are some people who are afraid by the commitment and say, no, this is a proposal that is not going to succeed because of this, and this. And there are other people who say, yeah, great idea, let's go for it. And you understand the difference. And it's extremely, you should have it clear in your mind. Creativity and innovation, of course, we look for creative people. Communication and collaboration. Collaboration, you know, today, it doesn't exist anymore, the figure of the person who works alone. I mean, it exists, but if you see the great innovations, the great advance, they come from mutual collaboration. Even artists today tend to work in collaboration. And the communication, you know better than me that it's important. It doesn't mean social media only. Communication can be done at different levels. And it is relatively easy to study compared to engineering. Studying communication, it's relatively easy. And but of course, you need to make an effort. Digital literacy is extremely important, and let me say, it is extremely important for an engineer to be able to code, whatever language. Unfortunately, the most efficient language is evolving. But for instance, I don't know how to code in Python, and I made a commitment with myself. By the end of 2024, I want to get fairly expert in Python, because I think I need to teach to students how to work in Python. And I am used to work in MATLAB and R. R is a software that is similar to MATLAB, open access. We will use R. I mean, coding is important. In the past, it was essential. When the digital world came about 30 years ago, we needed to code because there were no softwares. So even during my engineering studies, I needed to code. My final project was coding. And today it's less needed, but at the high level, you still need to code because it may be safer, more cheaper, safer than using commercial programs. So information literacy, media literacy, information communication technology literacy, these are important. And then career and life, flexibility, adaptability, initiative and self-direction, social and cross-cultural interaction, productivity and accountability, leadership and responsibility. Leadership is essential. It doesn't mean that you are ambitious. I mean, also ambition is not bad, but leadership doesn't mean that you are behaving like a boss. You know, leadership means that you may have also a low-profile approach, but you can lead an effort, you can lead a group of persons, you can lead ideas. This is extremely important, and everybody can be a leader. There is absolutely no, it's something that is accessible to everybody. Of course, a person is not a leader in everything, but in your specific field, if you are prepared, if you have a good background, you can become a leader. Okay, and then there is another thing that I want to tell you. What I would like to do in engineering is to focus on solutions. Sometimes in the past, we focused a lot on theory, and we didn't make in education the final step. The final step is indeed the technical application. And this is why I am making exercises, because I think we have also to keep in mind that as engineers, our job is to find is to solve technical problems, is to make technical applications. So this is something that brings to me to say that we should revert the workflow. We shouldn't start from the theory and go to through models and design variables to solutions, but we should start from the problems to the solutions that we want to find. It's not easy, so I'm not saying that I will follow this path in anything that I teach, but I will make an effort to do that. And this is my introduction, which once again, first link, you don't have to get prepared for your exam, but I hope it's information that is useful to you. Okay, let me go to the second link, which is the first real lecture, which is a premise, and I'm sorry for the two persons who already attended with me coastal engineering, because this is the same. But as I said, I will try to use a different and more updated wording. One thing, in any of the lectures, if almost all of them, you will find at the end of it a link to a PowerPoint presentation, which I am using to teach. This PowerPoint presentation is a synthesis of these web pages. And let me open it because otherwise it disappears. Okay, it's a synthesis of this web page. Of course, I cannot use this page, this web page to teach. It's too much text. For teaching, I can use the Blackboard or I can use a PowerPoint. My suggestion, don't use the PowerPoint for studying, because it misses a lot of details which may be asked, maybe subject for the exam. So the PowerPoint may be good for refreshing, it's good for teaching, but not for preparing from the beginning, preparing from scratch the exam. I hope it's clear. Okay, so let me start from costs, and you know why? Because harbors are located over a coastline. The coasts are an extremely important environment. They are natural environments, and their socioeconomic value is massive. They are extremely important. Coastal areas occupies less than 15%, more or less, of the Earth's land surface, but accommodate more than 40% of the world population. How we define the coastal area? Typically, it is defined starting from the coastline. So basically, let's check. Let's see if I can find out. You start from the coastline. So here you have the sea, and here you have the land. So the coastline is the divide between the sea and the land. And usually the divide is identified at the high tide mark. So we get the highest tide, not wave, okay, highest tide. And at the level of the highest tide, if we have a survey of the cross profile of the land and the bottom of the sea, we can identify the coastline. So basically, if you take a cross section, we have mountains, and typically we have the land that goes down, and then there is the sea, and here there is the sea. This is a high tide. So if I take the high tide, there is here a point that, if I put over a map in the horizontal plane, identifies this coastline. Okay. Given that I don't consider waves, it means that sometimes it may happen that we get storms and waves that go higher than the coastline. And usually this part of the land that is alternatively washed and dried may be covered by first by a beach and then by other elements like dunes, etc. And typically the vegetation adapts to this situation. So, but the beach, which is washed very frequently, you don't find any vegetation. But over the dunes, where the water gets there only rarely, only infrequently, then you get already some vegetation, etc. So this coastline is the divide, and the coastal area is defined as the strip of land that is 100 kilometers wide and within an elevation of, let's put it here, within an elevation of 100 meters. Okay. This means that you get the more restrictive of these two criteria. So if you go inside 100 kilometers, but after 100 kilometers, you get to an elevation of 1,000 meters, you are not in a coastal area. So you stop the coastal area, for instance, here, where the elevation is 100. Okay. And same thing, if you have the elevation of 100 that goes more than 100 kilometers into the land, you still consider it a coastal area. Okay, and oh, sorry, no, here it was wrong. If you have an elevation of 100 that goes more than 100 kilometers into the land, you stop at 100 kilometers, okay? And for instance, if you consider the Emilia-Romagna region, most of the Padana plain is located at an altitude that is lower than 100 meters. Okay, you get to Piacenza. Piacenza is still lower than 100, but it's not considered to be the Padana plain, the full Padana plain, a coastal area. We limit the extension of the coastal area to 100 kilometers. Okay, in this coastal area that we define in this way, live about 40% of the world population, and I would say that this figure reported here is a bit dated, because it refers to a situation where the world population was like 4 billions. Now it's about 8 billions. Okay, and in Italy, about 60% of the total population lives in coastal area, and about 1/4 of the Italian population lives in big coastal cities. It's clear why people live in coastal areas. It's clear because if you compare with living in the mountains, you understand the difference. Why people typically go over the mountains? They go there when there are wars, when there are problems, when they want to get isolated, or when there is no more opportunity to live in the coastal areas. But otherwise, people tend to live in the flat areas close to the sea, because the sea means opportunities for trading, for tourism, and it means generally easier climate. In the mountains, you know, there is a difficult climate, and in the coastal areas, the climate is better. And also, the area are typically flat. Not all the coastal areas are flat, but most of them are. So it means a flat area means that it's easier to make agriculture, to produce food. It's easier to communicate. It's easier to travel. So this is why coastal areas are important, because if there are no problems, if there are no other problems, people tend to live there. So you understand why also engineering of coastal area is important. And in fact, sea resources are really diverse. They include fishing, seaborne trade, as I said, tourism, and commercial activities. And coastal areas are not only facing seas. We have also in Italy, for instance, big lakes, the pre-alpine lakes. We define the shoreline of Lake Maggiore, Lake Garda as coastal areas, and because they have all the features of typical features of coastal areas. There are in the world only 48 countries which don't have access to the sea. They are called landlocked countries and are known to be disadvantaged. In fact, there is a reason why only 48 countries are landlocked. I think I have a map here. Let me see. No. I show to you the map. This is the map of the landlocked countries. I think this graph comes from some years ago, but there is a link here which opens a Wikipedia page, and this is the updated map. They are known to be disadvantaged, and they are only 48 because several countries made an effort to gain access to the sea. And also, in the case of the war between Russia and Ukraine, you know that it's a strategy to try to occupy the coastal areas. You may have heard this. And it's clear, because if you deprivate a country from an access to the sea, you cause a big damage for for the limited access to these resources which we were discussing just now. So coastal areas are extremely important, and this is why we, just one second, I go back to the presentation. This is why we are interested. Now, we already defined the coastline is the line that forms the boundary between the land and the ocean or sea or lake at their high tide mark. The coastline cannot be precisely determined. When I gave to you the definition and I said high tide mark, you understand that defining the high tide mark is already a problem. But the main problem is that if you want to plot the coastline over a map, it depends on the scale of the map. So if you get the scale very detailed, the coastline gets longer. And this is called the coastline paradox. It means that you cannot give a measure to the length of the coastline because it depends on the scale of representation. This is related to the theory of fractals, which you may know, may not know, but the fractals are figures that keep the same shape if you zoom over them. Okay, and let me try to find a picture of a fractal. And I think it is interesting because the coastline is supposed to be a fractal form. Fractal. And images. One second. Okay. So if you look at this, this is a fractal. If you zoom over, second. If you zoom over this figure, you continually get the same picture. If you zoom out or zoom in, it's called to be a scale invariant figure. And the coastline is supposed to be scale invariant. It means that if you increase, if you zoom in, you get the same shape, which means that the length is continuously increasing as you zoom. We can close this. The theory of fractals was very popular 30 years ago. This is just out of curiosity because there were important scientists that proposed to study almost every natural process with the theory of fractals because they supposed that many natural geometries were described, were scale invariant, were described by fractals. Actually, they didn't really succeed. But for the coastline, indeed, this is supposed to be something that is close to fractal. So basically, you cannot give a length to the coastline, but on the other hand, when you fix the scale of the map, you can measure the length of the coastline. And it is interesting to look at an important parameter. I go back to the page because there is a Wikipedia page which is interesting. Here, for instance, you can see the description of the coastline paradox or the fractality of the coastline. You see on this figure on the left, you see a measure of the coastline that is taken by using a coarse scale of representation. Coarse means that the scale is very large, you zoom out. So if you zoom out a lot, the coastline, the shape of Great Britain, can be depicted with the left figure. If you zoom in, you get the figure on the right. But if you zoom in once again, and you see that from the left to the right, the length of the coastline is increased. But if you zoom in again, the length of the coastline keeps increasing. Okay. And but if you fix the scale of the map, you get a measure. And it's interesting to see the coast area ratio of countries. Coast area ratio means that you take the length of the coastline and divide by the area of the country. And if you divide by the area, you get a result that is expressed in units of meters divided by kilometers, typically. If you divide by the square of the area, you can get a dimensionless measure. Now, if you look at the world, first of all, there is the problem that the area of the country is uniquely defined, while the coastline, the measure of the coastline, depending on the scale of representation, is different. So here, this table makes reference to two measures of the coastline of each country: the measure given by the World Fact Book, which is a database, and the measure given by the World Resources Institute. You see that indeed there is a big difference, because if you look at the World Fact Book gives a length of the coastline for the full world of 356,000 of kilometers. If you look at the World Resources Institute, the length is 5 times larger, more than 5 times, because they use a different scale. And maybe they also considered internal lakes, while I'm not sure if this is the case, but maybe that the World Fact Book didn't consider it. Anyway, the coast area ratio for the whole world, it's, if you look at the coast area ratio, cost divided by area, square root of the area, you see the whole world has 30, around 30. And let's look at the last column. And you see the countries have very different coast area ratio. Canada has a coast area ratio, coast square area ratio of 67, which is lower than Norway. And this is what you would expect, because, of course, Norway is an island, and islands typically have a larger length of the coastline. Anyway, this coast area ratio is considered to be an indicator of opportunities, of resources. The countries with the larger coast area ratio, in principle, are supposed to have more opportunities for exploiting resources. This gives to you the idea of the importance of the length of the coastline. It's time to make our break. When I make the break, I close the webcam and the Allora, so okay, so we know why coastlines are important, and in order uh, to put us in the condition of studying coastlines and therefore making projects in order to protect coastline or to locate harbors, we need to understand how they evolve and how they modify their shape and how they are formed. The coastline is the result of an interaction between deposition of sediments and erosion by the sea. There are several different types of coastlines, and they are all exposed to erosion by the sea. Erosion takes place through the action of waves, typically, and it's a process that we can classify as intermittent. Erosion is a long-term process which is characterized by spikes. When extreme events occur, then we get extreme waves and extreme erosion. So it is a process that is continuous in time, but in a way it's not stationary. It's characterized by peaks, by extremes, by sudden changes, because erosion can also give rise to landslides, to very major modifications. And there is also deposition of sediments. Deposition of sediments operated by the rivers. In any coastline, we have rivers that bring to the sea, of course, water, but with the water, sediments. And these sediments form the beaches. And depending on the shape of the coastline, the beach can be continuous or can be even the beach intermittent with some spots with the presence of sand and instead spots or chunks of coastline, pieces of coastline where we have rocks that are directly facing the sea. These processes are natural processes, but are influenced by human activity a lot. And this is why we talk about preservation of beaches. We talk about beach protection, beach recovery, because the human intervention modifies the evolution of coastline, modifies the shape of the coastline, modifies the delivery of sediments by rivers, and therefore it's impacting the environment of the coastline, which is extremely delicate. When we study something, a natural form, usually the first thing that we do, the first step in order to understand these forms is to classify them, because based on the classification, we can move towards an understanding of the evolution of these natural elements. And there are different criteria proposed by the literature for classifying coasts. There is a very popular criteria, widely used, which splits the coastline in two broad categories. The category, or let's say, first of all, let's talk about the categories of the criteria. We can use different criteria to classify coastline, and we can split them into two categories: descriptive criteria, which are based on morphological features of the coastline. Another category is the category of the genetic criteria, which classify the coastline on the basis of its origin, how the coastline was originated. And first, descriptive criteria allows us to divide the coastline in two categories: the cliff, the coast, and the flat coast. The cliff, the coast, prevails where mountains directly face the sea. And therefore, we have rocks, we have walls that are going directly into the sea. Typically, in these conditions, you can find pocket beaches where the rivers enter into the sea or the ocean. And these pocket beaches are a very delicate environment because they are a very small, a very small spot, which is the result of the compromise between the erosion activity by the sea and the position of the sediments. And usually, when the coast is cliffed, the rivers are small rivers entering into the sea. It is unlikely that a very large river enters into the sea through a cliffed coast. Why? Because the very large river typically brings a lot of sediments and therefore tends to advance into the sea and to form a delta, typically. In some cases, we have estuaries even for large rivers, but even in this case, the delivery of sediments tends to bring the river into the sea through a flat area. So if the rivers that enter into a cliff coast are small, you understand that it's more delicate also their environment. So a human intervention that causes change in the delivery of sediments, for instance, some stabilization of the hill slopes, can change also the ecosystem and the shape of these pocket beaches. The flat coast, it's originated by deposition. It has a mild slope. And for instance, the coast here in Ravenna is a flat coast, which is the result of the delivery of sediments by the Po River. The Po River, filled what was an ancient gulf. The Padana Plain was in ancient times a gulf and was covered by the Adriatic Sea. And then the Po River brought down a lot of sediments and filled all the plain with the sediments, originating first an area that was covered by marshes. It was inhabitable because it was unhealthy. And then since the Etrurian times and then through the Romans and the other civilization, this area was reclaimed, was drained, and transformed into a very fertile area. And the result is that the slope is very mild because it was filled by the sediments of the Po River. And the beaches that you can find here are characterized by very fine sand. It's the result of the advance of the river because the deposition of sediments by the river is gradual. First, the larger boulders, the larger grains are settled down. They settle down. First the gravel, first the large grains. If you go in mountain rivers, you see that the sediments are large boulders. If you go in the downstream part of them, you see that the size of sediments progressively reduces. In the case of the Po River, after 200 kilometers through the Padana Plain, the size of the sand that you can find here is very fine. And it is very profitable for tourism, for leisure. On the other hand, can be easily eroded. So you understand that this equilibrium is delicate. It's delicate because it's delicate like in the cliff coasts. It's delicate because along the course of the Po River, in the Po River basin, there are a lot of human interventions in order to reduce the sediment transport, because the sediment transport of the Po River is a problem, because the riverbed gets higher and higher and gets more elevated with respect to the surrounding areas. And therefore, given that we want to keep the Po River in the same position, we don't want the Po River changing its course like it did in the past. We want to reduce the delivery of sediments. On the other hand, reducing the delivery of sediments causes a shock in the equilibrium of the coastal areas. So it is a complex process, a very fascinating process that it's modified by human intervention. And in response to our modifications, we need to make other modifications. So as a result of a decrease in the delivery of sediments from the Po River, now we have to protect the beaches against erosion. And for instance, in some cases, we replenish the beach with sand. So we substitute artificial replenishment. We substitute the delivery of sediment by the Po River. to compensate the intervention that we made upstream along the Po River to reduce the delivery of sediments. So you understand that after human perturbation, often we have to intervene with a kind of counter perturbation in order to compensate for other perturbation. So once the environment is artificially modified, we need a continuous action to take care of it, to keep it in an equilibrium situation. So when we compromise an equilibrium, we have to make another intervention, a corresponding intervention to re-establish the equilibrium. And understanding these processes is our job. So as offshore engineers, and engineers who take care of harbors, we need to intervene on these processes in order to keep the coastal areas and then the harbor in a situation of equilibrium. It's a very interesting assessment that we have to make, which is subjected, I want to anticipate that, to a lot of uncertainties. In any occasion that we have to interact with nature, we have to accept that there is uncertainty in the evolution of nature. Think of rainfall, think of river flow, think of waves. You can predict waves, but there is uncertainty. And therefore, it's also our task, it's the typical task of the engineer to deal with these uncertainties. Typically, we introduce safety factors to deal with uncertainties. But in some cases, we need to do something more because safety factors may be not enough, or may imply other problems, other negative impacts, which we will discuss. And if we use the genetic criteria for classifying the coasts, it's extremely interesting to divide the coast between emergent and submergent coasts. The emergent coasts are the result of an uplift of the land. The submergent coasts are the result of an increase of sea level. So you can understand that the shape is quite different, because if we have land that emerges, the new coast was shaped by the ocean. So the new land that was submerged was shaped by the oceans. If we have a submergent coast, it means that the new coastline was shaped over the land, and then it was drowned. It went underwater. So the shape is different. And not only the shape, it's also different, not only the shape of the coastline, it's also different the profile of the sea bottom. And for instance, I want to give you an example. Emergent coasts may be characterized by the presence of rocky cliffs and flat platforms. If you think of a land that emerges, you may have had earlier a flat area in front of the sea that emerged. And therefore, this flat area is now more elevated. And you may have instead a very steep coastline landwards, because it was the part that was originally submerged and subjected to the erosion by the sea. Instead, an example of submerged coastline is the Chesapeake Bay in the west coast of the United States. You see the shape of the coastline. You can recognize valleys that were carved by glaciers and now are filled up by water. And clearly, it's a pattern that has a unique feature. The shape was given by the erosion of glaciers, by erosion over land. So you can recognize river valleys there that were filled up by water. This is particularly very interesting case because Chesapeake Bay is an area that is extremely relevant from ecosystemic point of view, and today is particularly important for tourism, for leisure, and there are important programs for restoration. if I'm not wrong, if I will remember, I have a video linked somewhere here. Which describes the restoration program of the bay. Let me see. It is somewhere here anyway. But I don't think it's important that we look at this video now. I just wanted to point out to your attention that it's a video that is interesting because it describes what actions they are taking in order to restore the beach. Okay, let me go back here. Beaches have a very important social function, and they are also very important from a socio-economic point of view. There is a relevant topic of research today, which is assigning an economic value to beaches. And it's an open problem, like assigning an economic value to cultural heritage. In Italy, this is an important problem. Beaches are part of cultural heritage. In general, assigning a value to cultural heritage is interesting. It's an interesting problem because cultural heritage is traditionally considered an intangible value. Intangible means that you cannot monetize it. And also for beaches, and we realize that for some reasons, they can be considered an intangible value. On the other hand, we have the need, in order to make plans to preserve beaches, to restore beaches, we need to give a socio-economic value to them. And so there are attempts to try to monetize at least part of the services that are given by beaches, like, for instance, the commercial services in terms of trade, exchange of goods, and protection against natural hazards. Here there is a spelling error, like protection against tsunamis, and also their importance for the leisure of people and therefore their health. So it is an open problem, a problem that is subjected, as I said, to research activity, to research effort. And in order to estimate with the cost-benefit analysis, to estimate the priorities of selected interventions. Ecology of beaches, and I'm coming close to my conclusion of this introduction. Ecology of beaches is another relevant matter because you may think, if you go to a beach, for instance, here close to Ravenna, a beach that is used for commercial purpose, you may think that it is like a desert area. There is no ecosystem within it. And indeed, this is partially true, because the works that we do in order to make a beach usable and adapt for tourism, indeed requires a continuous movement of sediments, a continuous displacement of sediments. Every night during the tourist season, people go there and they re-establish the flat shape of the beach. In doing that, indeed, we destroy the ecosystem. We basically, in moving continuously the sand, we don't allow the ecosystem to survive. Also, if you think at the beaches here, typically they are scraped during winter. What does this mean? The sand is brought back far from the sea in order to avoid erosion, and then it's displaced back in front of the sea when the tourist season starts. If you go to see the beaches of the Adriatic Sea now, you will see that most of them have the sand brought back. This is called beach scrapping. And then it's brought back close to the sea, as I said. But in doing so, we destroy the ecosystem. But actually, in their natural form, the beach is a very living environment. Even if you don't have vegetation directly in front of the sea, you have a lot of microorganisms living within the sand, like bacteria, like phytoplankton, and also macrofauna, like turtles in the natural environment, are living on the sea. They go there also for fishing, for finding food. There is an ecosystem that is indeed living and important for the preservation of the sea environment, for the removal of organic matters that are brought by the sea. The bacteria is extremely important to degrade this organic matter. So they help in keeping the beach in an equilibrium situation. Once that we remove the ecosystem, then we have to compensate by removing also the organic matters, by removing the litters, etc. And this ecosystem is also important for limiting the erosion, because it is true that directly in front of the sea you don't have vegetation, but as soon as you get a few meters from water, you can get some vegetation over the sand, and this vegetation helps in limiting, for instance, wind erosion, sea erosion. It's extremely important. And also keep in mind that into the beach, we are used to think that in the underground there is salt water. But if the beach has a minimum of slope, if it is very flat, it is true that in the underground there is only salt water. But with even a minimal slope, in the underground, we can find an interaction between fresh water and salt water. Once I went to a beach in Greece, it was an island, and the beach was really almost flat, but with just on one side, a little bit of slope. And an olive tree was there 2 meters from the sea, from the seawater. And clearly, and it was quite a huge olive tree. If the olive tree could survive there, it means that in the underground there was fresh water flowing towards the sea, which helped to push back the salt water. There is a continuous interface in coastal area between salt water and fresh water in the underground, fresh water that comes from the land. And this is also an important process that you have to understand, because saltwater intrusion and the pushback of salt water by fresh water are what determine the growth of vegetation and, perhaps more important, our capability of getting fresh water from the underground, from wells. This interaction is extremely interesting. Here it is described, this interface between salt water and fresh water. You see that there is an interface. Here it is depicted like a line interface. Actually, it is there is some spreading. There is a mixed zone, okay, of what is called brackish water in the underground. But indeed, there is a kind of interface which is the result of a compromise between the flux of fresh water and the intrusion of salt water. What you can understand from here is that if you have a sea level rise, it means that salt water intrudes more. If you withdraw fresh water, it means that salt water intrudes more. So we need to understand this compromise, the dynamics of this interface between salt water and fresh water. Okay, the evolution of the coastline, the evolution of the morphology is studied by this discipline, coastal hydrodynamics and morphodynamics. We will not study it because it's not pertinent to harbor engineering. But I just want to give you this information. When you listen of coastal morphodynamics, it means the study of the evolution of the shape of the coastline. We need to study the erosion by the sea. We need to study the flux of sediments by the land, write equations that make the balance between these two components. There are commercial models that may help us. It's a very interesting problem. There is uncertainty in doing that, but it is also necessary in order to make interventions like locating harbors, locating beach protection structures. Usually, when you go for a new project regarding an harbor, if the project is important, the authorities ask you to make a model of coastal hydrodynamics and morphodynamics to study how the harbor will impact on that. There are several cases of harbors that were created and had a strong impact on the surrounding coastline, and this impact is to be understood. Okay, I think we can stop here because this is related to things that you already know, because I think you have already studied how to characterize waves, what are the basic parameters that define a wave shape, and etc. Am I correct? You already studied wave mechanics, okay? But you didn't study it? Okay, and what about the other students in structural, or did you have a background on wave mechanics? No? Okay. So if I talk about wavelength, wave amplitude, these are unknown terms to you. Okay. It's not a big problem because we don't use this, okay. But I keep it in mind. I think we make a limited use of wave forcing in this course, but there is a part when we estimate the loads on ports, there is a part which assumes that you know about wave forcing, and then you know this terminology. But we will make some. I'll give you some information. Okay. For now, I think we can avoid this slide because I don't want to anticipate things that require a long discussion. Okay, do you have any questions so far? No questions? Okay. Now, we may move forward with the next link. Just 1 second, I want to make sure that, let me just give you some numbers because they are not included here, about the social function and value of seaports. And the numbers that I want to tell you are the figures of the Port of Genoa. In terms of activity, so the Port of Genoa exchanges moves more than 51 million tons per year of goods. About 6,000 docks per year are registered. About 4,000 day cars and trucks in, out, into, from the port. About 3,000 day trains in, out. About 2,400,000 containers a year in, out. About 3 million passengers a year. So these numbers, I think, sufficient in giving you an idea of the importance of this port from a socioeconomic point of view. And it's one of the most important, if not the most important port of Italy in terms of these figures. So you understand that we are talking about things that have a relevant socioeconomic impact. And also they have an history. So the history of ancient civilization is characterized by the presence of port which played a relevant role. Let's think, for instance, of Venice. Venice based its power, the old Republic of Venice, on trade, and therefore the port activity. In fact, they diverted the Po River. Venice is not listed here, but Venice, to give you an example, which I think is important, they diverted the mouth of the Po River because the Po River was advancing into the Adriatic Sea a lot. And in the past, it was estimated an advance in the sea of 70 meters per year. So you understand, 70 meters per year. So it means that you could see by eyes the Po River, the land, the delta moving forward. And Venice was concerned by the fact that it could close the Venice Lagoon. And so they diverted the mouth of the Po River south. And what we see now, the delta of the Po River, is the result of this shift that was operated by the Republic of Venice in, I think it was 1576, something like that. And also, if you look at the ancient civilization, as I said, you see that each of them has an important port. So China, Egypt, Greece, India, and Rome. It is indeed an important issue. Let me see if this link is still working, because sometimes I need, okay, it's still working. And this is an interesting book that is available online. It is not very technical. It refers on economics, management, and policy, but it is indeed interesting, and it's recent. It's quite recent, 2022. And it is, I think, an interesting reference. It's not really used by me here because, as I said, it's not very technical. In my web pages, I try to use only open access material. So it is my purpose to teach and to deliver these subjects by using open access material only. So this is why you can find this link here. Okay, we already talked about ecology and the social function of beaches. You see here a nice picture. You see, this is a beach in Germany. You see vegetation. It is very close. And vegetation, you see, it's placed at an higher elevation with respect to the beach. The fact that there is this high elevation is the reason why you have vegetation, because the sand can accumulate fresh water, and vegetation, of course, can only grow up if there is some fresh water in the underground. So it means that when it rains, through infiltration, fresh water gets into this sand, because we have sand beneath this vegetation, and remains trapped there for a while. And this is called, this higher elevation is called the dune. This is something that I usually teach in coastal engineering, so I'm not, don't worry if to learn about the shape of beaches. It's not a subject for us. But I think it's important to know the basic elements of it. The dune is the result of the highest storms. So the sea, when there are very large storms, very high waves, brings the sand from the seashore to inland and forms the dune. The transportation of sand from the immediate closeness of the sea to some meters landward forms the dune. The dune marks the limit of the highest waves, of the extreme storms. And the dune is an essential protection for the land in terms of protection from wind, protection from tsunamis, protection from ice storms. And the presence of vegetation makes the dune more resilient to these extreme events. Okay, I think here we saw everything. Let me see if I missed some figures, some pictures. Let me see. Okay, this is an example of a beach in flat coast. And you see these protections here. These are called groins, and they have the purpose of limiting the erosion of the beach. In particular, the erosion caused by waves that run almost parallel to the beach. It's called along coast waves. along a coast sediment transport. If you make these structures, which are perpendicular to the main direction of the coastline, you trap the long-shore sediment transport and you favor the formation of beaches because sediment trapped form the beach. In order to form your background, it's extremely important that you look at these shapes, that you try to establish a connection between what we discuss and the real world, what you can see. And it's not necessary to physically see. We have the advantage today that we can travel everywhere in the world with just few clicks. So navigating the web, looking at pictures that you can find in Google, and looking at videos, it's a way to increase your experience. And where you can, try to go there and look with your eyes, because of course the direct assessment is much better than a virtual assessment, but still the virtual assessment is important. And I myself try to look over the web for material for teaching, but also material that I use in order to improve my experience. And it's a fortune that today we can really travel everywhere. Okay. Let's go back here. So before moving forward with the links here, I want to make a parenthesis that usually I don't make here. And a parenthesis that it's not something that you have to consider for preparing your exam. So I don't put an additional link here, but I go in the webpage of my other courses to open a presentation that gives to you this parenthesis that I think we can use until the end of the lecture today. So just let me go back to my website, 1 second. This parenthesis is focusing on climate change. And you see, this is an introduction to other courses, but let me just, move here from the second slide. And why climate change? I think there is no need to explain you why. Climate change is becoming today an extremely important issue, and especially for the sustainability of coastal areas. It's becoming extremely important. And it is extremely important, but on the other hand, we still know very little of it. And especially in technical terms. In technical terms, I can, to simplify, say that we don't know anything. So we have an idea of what climate change is. We have an idea of the causes. We have an idea of the solutions. But when an engineer is called to make a design project under climate change, still a big question mark opens. And this is why we are trying also to offer some curricula in civil engineering and environmental engineering that are explicitly focusing on climate change. So I just think it is worth giving to you an overview of what is the science of it and what is the technical implication of climate change. I think we can take these 40 minutes I think they are well spent. First of all, what is climate change? Look at the left graph, and it represents the monthly temperature anomaly. Anomaly means that instead of depicting temperature, you depict the difference from the mean. So here you have temperature monthly from January 1880 to December 2022. You compute the mean, and then you display on the graph the difference from the mean. And you see that there is, there are up and downs, but there is a steady increase. This is called global warming. Global warming took place especially in the past, starting from 1990, so in the past 35 years. You see that the steep of the graph is larger in the past, let's say from 1985. Before than that, from 1950 to 1970, there was a small decrease in global temperature. In fact, at that time, people were concerned by cooling rather than warming, but then in the past 35 years, temperature increased. And what is the source of this graph? It's our world in data. Keep in mind this website because it gives to you a lot of data related to sustainable development. So this is the global warming. But if you look at the categories of data that you can find here, which you can find at the global level and the country level, so it's extremely important. The categories are browsed by topic. You see population and demographic, health, energy and environment, food and agriculture, poverty, democracy, human rights, violence and war. It's extremely interesting. For instance, if we look at population growth, you see here the graph, and it focuses on some countries only. You can put the world here. Of course, if you put the world, you can play with these graphs. It's really interesting, and you can get the table. If you put the world, of course, the scale is larger, and therefore you can see you cannot see the details of the countries. If you remove the world and you remove, for instance, China and India, you can see the progress in United States, Indonesia, Pakistan. And it's interesting if you put Italy here. And in Italy, you can see what we know. Since 10 years ago, there is a demographic decrease, which is quite significant. Actually, it's only in the last 30 years because we had also a stable situation between in the 1980s and 90s up to 2000, and then an increase, and now a decrease. This is just an example. You can also play with the time lapse. So these graphs are interactive. And if you look at this information, I think for an environmental engineer, offshore engineer, there are information that are really interesting. It's information that is, as I said, focusing on sustainable development, not really engineering, but there are a lot of numbers that are interesting. So now, again, the graph of global warming. Of course, you may say, yes, there is an increase in the past, in the recent past, but it may be natural. Indeed, we had similar increases in the past. In the end, we had in 1200, around 1200, during the so-called medieval warm period, we had a higher temperature at the global level than today. So one may say, okay, maybe it's natural. On the other hand, if you look at the progress of demographics in the same period, you can find a similar trend. If you look at the progress of water usage, the scale of the graph is a bit different. It starts from 1901 to 2014. Water usage is the right graph. You see a similar trend. So it is quite likely that there is an association between these variables: increasing temperature, increasing water usage, increasing demographic, increasing many other things. In fact, the term great acceleration was coined to indicate the increasing trend in various measures of human activity that occurred after the Second World War. So this association, this great acceleration of several indicators of socioeconomic development may point out that there is a connection, that the global warming is caused by humans and human activities. Part of them, I mean, may be the result of speculation. Part of them may be an unavoidable implication of increase in demographic. And here, great acceleration, there is a Wikipedia page which you may consult if you are interested, socioeconomic trends, Earth system trends, etc. Okay, so 1 second, because can't find anymore the presentation. I think I closed the wrong, just give me 1 second. I think I closed the wrong window. Let me go back. Okay, let's do this and this and this. Okay, now, what is climate change? I don't want to take much of your time, so I anticipate that this is an interactive presentation. You can play with it by yourself if you are interested. This presentation is accessible on my website. If you click on the courses focusing on climate change, which are just above the course on Harbour engineering, you can find it. So climate change is defined as a long-term shift in weather patterns. So this is the definition. So climate change is defined as a long-term shift of weather patterns. And what is climate? What is weather? Weather is the day-to-day variability of variables like temperature, rainfall. So we talk about weather when we talk about meteorological prediction. We predict the weather, the day-to-day change of variables. Climate refers to the statistics of weather. So the weather variables are averaged over a long period. And therefore, the average value defines the climate. And for instance, rainfall, daily rainfall, the rainfall today, which is 0, is an expression of weather. If I say that the mean rainfall over Ravenna is 800 millimeters per year in the period 1990-2020, this is a climate variable, a climate feature. So if we say today is too warm, this is climate change, no, it's not correct. We have to compute the average over a long period, and which is conventionally fixed as at least 30 years by climatologists. So when we talk about climate change, we need to be aware of what it means. Another important thing, you have to distinguish between change and variability. This also with waves. Climate change implies also a change in the waves feature. And change means a long-term shift. Variability means up and down. And you can see here the graph of two variables. It's temperature change in tropical America and Northern America. There is an increasing trend in both of them, which is the result of global warming. But Northern America is much more variable. Why? It is important that you understand variability. It's important because the presence of variability makes the identification of climate change more difficult. Because, you know, identifying a trend, you see the blue line, okay, I see a trend, I do see a trend, but on the other hand, it's not so clear. With the red line, I have less variability, the trend is clearer. And variability implies cycles, up and downs in the short term. In the long term, variability implies that everything is stable, unchanged. But in the short term, if you take a short window, variability means up and down. So is the current global warming an expression of variability rather than change? Probably not. Probably it's change, but actually we still don't know. Another thing, how it is global temperature measured with thermometers, ground thermometers. And the number of thermometers changed during the so-called instrumental period. We started measuring temperature at a global level in 1850. This is why you don't find the temperature values before 1850. And the number of thermometers is changed along the period. And we have more thermometers in the northern hemisphere than in the southern hemisphere, because in the southern hemisphere, there are a lot of oceans. It's important also to know when you see any information that you have to use, when you see an observation, when you see a number, you have to know how the number was measured / derived. You have to get, as an engineer, an idea of its uncertainty. So global temperature, you are an engineer, you should, as soon as possible, wonder how it was measured. This is why I am telling you. If you get observations on waves, wave forcing in a place, you should wonder immediately how the waves were monitored. It was a remote sensor. Was it a direct observation by humans? You have to get an idea of uncertainty. Uncertainty for an engineer, it's essential. Okay, again. So, what is the reason why we think that humans are responsible for climate change? As you may know, a large part of the scientific community is convinced that humans are responsible for climate change. It's a logic intuition from the observations of the Great Acceleration. The public is less confident. And while most of the scientific community is convinced of that, the public is less convinced. And there are reasons for that, which we don't discuss here. And so it's important to wonder what is the proof that the scientific community uses to state that humans are responsible for climate change. First of all, why the question is important? The question is important because to solve a problem, an engineer knows that we have to identify the causes, the reasons for the problem. Otherwise, you can't identify the solution. It's like a medical doctor. If a patient is suffering, the first thing is to understand why, the reason, because the cure is different, okay? So we have to understand it. Second question, why it is controversial? For obvious reasons, it's highly controversial. Highly controversial, this question. Why? Because one thing is something that is occurring naturally, and another thing is something that is occurring for our responsibility. So there are political implications, economic implications, and it's much more controversial than discussing of a flood, because the flood is local. Global change is global. Climate change is global. And there are impacts of climate change in other continents with respect to the continents where climate change has potentially been triggered. I say potentially because we are not sure that humans are responsible for it. Scientific community believes that indeed humans are, but it's a question that is controversial. So what is the explanation? This is, again, a quiz, but the correct answer is the first one. It's models, the explanation. Climate models cannot explain current climate change unless anthropogenic forcing is considered. This question and this correct reply is extremely significant for an engineer. Why? Because an engineer, the ethics of engineering suggests that we trust data rather than models. Models are an aid to support what we can understand from observations, from experience. It shouldn't be the other way around, that we trust on models and use the data for confirmation. This implies the responsibility of an engineer. This is something that often is not considered. So it happens quite frequently that engineers express doubts on the human origin of climate change. Why? For the simple reason that I just mentioned, because engineers tend to look at the data first and then to models. They don't trust models blindly. this is another important consideration. So what I'm saying from an engineering point of view implies that if you have to solve a problem, if you have to make a design project to adapt to climate change or mitigate climate change, at least you should make an assessment by using data, if available. Make an assessment using models and take the safer, at least. But you cannot trust models blindly, because if you make a mistake, then you are sued and you have to defend what you did. And defending means that you cannot say, I trusted my model. Okay, this is extremely interesting. I mean, one thing is to look at a problem with the eye of a scientist. Another thing is to look at the problem with the eyes of the engineer. And the problem is also more complicated because today engineers are also scientists. So it is a philosophical problem, which has important technical implication. Some numbers. Climate change. Global temperature has raised about 1.3 degrees since 1880. Keep in mind the orders of magnitude. There are people saying 10 degrees more. Absolutely not. There are people saying no temperature change. Absolutely not. 1.3 is the correct number. The order of magnitude is 1. Okay, not 10, not 0. Temperature increased more in the northern hemisphere. We don't know why. Maybe the reduced density of thermometers. Sea level rise, this is relevant to you. From 1880 to 2020, 21 centimeters, not meters, okay? Because, you know, sometimes we listen news which say some islands are going to be drowned. Unless something really unprecedented happens, we cannot expect in the next 100 years meters of sea level rise, unless something of really unexpected happens. Our observations say that from 1993 to today, under global warming, the sea level rise has been something like 15 centimeters. So indeed, after global warming, the trend in sea level rise is increased, but still the order of magnitude is, I think it is 3 millimeters per year. Okay. So global CO2 emissions have raised from human emissions from about 5 to about 35 billions of metric tons from 1940 to 2020. If we look at the emissions per capita, because meanwhile there has been an increase also of human population, increased from 2 tons in 1940 to about 4.5 in 2020 tons per year. Okay, it's not specified here, but it's tons per year. CO2 concentration in the atmosphere increased about 25% from 1980 to 2020. We have not yet reached the 2 CO2 limit. Global economic losses from weather catastrophes are about $3 billion of US dollar. 2023 has been the hottest year on record at the global level, starting from 1880. And the global population is increased from about 2.5 billion in 1950 to about 8 billion today. Okay, let's move forward. Negative impacts of climate change. Let me discuss a little bit. Global warming, it's an impact, and it has an impact on several things. But let me say that some features which I think are important for an engineer. Global warming is not uniform. There are hot spots. For instance, the Alps warmed about 2 degrees. We don't know why. Global warming is changing the seasonality. You know that we say we are moving towards a tropical weather, which means different seasons, different features of each season. And in particular, what we have noticed in terms of water resources, and also in terms of waves, wave weather, we have noticed that the winters are warmer. And the fact that the winter is warmer, it means that we get less snow and more liquid rain, which means, and also we have an anticipated snow melt, which means that we get more flow in the spring, for instance, in the Po River, and less flow in summer, which is a problem because we need water in summer, not in spring, for irrigation. So global warming is one of the impacts. Weather extremes, we believe that rainfall extremes have increased under global warming. How much? Another order of magnitude that is important. About, there are some theories which predict that for each degree of warming, heavy precipitation may have increased 6–7%. Indeed, this is what we observe. If we look at extreme precipitation data, not models, data, we see an increase from 50 years ago of about 5–10%, depending on the location. And it's not twice the previous situation, the previous extremes, not 3 times, not 10 times, like sometimes I read on the media. Still, 20 centimeters of sea level rise are important for saltwater intrusion. Still, 10% more rainfall. In some cases, it doesn't matter. It doesn't have any implication. In some other cases, it may imply that some thresholds, for instance, for floods, are crossed. So it really depends on the local situation. Another important consideration, the impact of climate change depends on the local conditions. So in some countries, some contexts, no matter climate change, people may even benefit from it because maybe they are resilient or because maybe they benefit from an increase of temperature. In other conditions, other places, instead, even a small change in climate may trigger disasters. These mechanisms are largely unknown and are the subject of ongoing research. Some of them, we get the connection in a quantitative way, but in order to make design projects, we need quantitative assessments, and in most of the cases, they are missing. Keep in mind, under climate change, you will not find guidelines. Same situation for harbor engineering. We will see that in certain countries, there are no guidelines, no legislation on how you have to make a design. In this case, you have to use your creativity and your sensibility to adopt safety standards. Okay, interesting problem. And you can see some job opportunities. Non c'è problema. Grazie. Ci vediamo. See you next Wednesday.
Yes, thanks.
Yeah, no problem. Negative impacts of climate change, floods and droughts. This is a direct consequence of the increase of rainfall or decrease of rainfall. And indeed, we have the feeling that flood and droughts are increasing their impact. But there are a couple of considerations that I want to make. First of all, floods. Floods, we observe from data an increase of flood frequency in small rivers, not large ones, at least in Europe. So it means that probably climate change is impacting in a different way large rivers like the Po and small rivers like mountain creeks. We have an interpretation for this because probably climate change has changed only the short time rainfall, the rainfall, very intensive rainfall that lasts for a few minutes only. And this is the type of driver for small-scale floods. Large rivers, large-scale floods are triggered by long rainfall that lasts for like 1 week. The Po River is not sensitive to 1 hour of rainfall. It's sensitive to a rainfall that lasts for 1 week, maybe weaker rainfall, but extended in area and long-lasting. So this may be the explanation. So what has been impacted by climate change may be short-term rainfall and a short spatial scale, small spatial scale floods. Droughts, it's not clear if rainfall is decreased, but it's clear that droughts are affected by global warming, not only through rainfall. I made the example of snowmelt, for instance. So while it's not clear that we have droughts in terms of rainfall more, it's clear that we have droughts in terms of river flow more frequent, where river flow is also determined by snowmelt. I hope that this consideration give to you the perception of the complexity of the problem, and a problem that shouldn't be oversimplified. Another situation is the hurricane, another threat. It's not clear whether hurricanes are influenced by climate change. The IPCC, which is the International Panel for Climate Change, believes that indeed it's likely that there is an influence, but NASA, no, sorry, the opposite. NASA says that it's likely that there is an impact. IPCC says that it's unlikely. Now, sea level rise, and this is directly interesting for you. Basically, global average sea level has, as we have already discussed, have risen about 8-9 inches, so 21-24 centimeters since 1880. And in 2021, global sea level set a new record high. The rate of global sea level rise is accelerating. It's about, as I said, around 4 millimeters per year. Sea level rise is not constant because the topography of the ocean surface is not constant. And high tide flooding seems to be increased with respect to 50 years ago. And the negative effects are related to injuries, related to coastal flooding. This is not really very relevant. Stress, again, it's not high priority. Salination of coastal water and destruction of coastal ecosystem are high priority impacts. Stress is less priority because it's not yet widespread. Positive impact of climate change. There are positive impacts, and I leave to you this slide to read. And because, first of all, in warm weather, people usually live better. Prosperity is favored by warm weather. And also agriculture may benefit from a longer season, or longer growth season. And also crops may benefit from an increased concentration of CO2. CO2 is a fertilizer. Tourism may benefit from a longer season, not skiing. And also shipping commerce may benefit from the possible opening of the Northwest Passage. And north regions may benefit from an expansion of agriculture. Keep in mind, usually the human population, humans, reacted to climate change in the past mainly through migration. So climate change has also occurred in the past, and it occurred and people reacted through migration. For instance, we know that humans migrated from Africa and Australia towards the north after a warming. On the other hand, migration takes time. So if climate changes in a short time, there is no time to adapt. The social system doesn't adapt, which means wars, tensions, at least wars, maybe, which is something that it's also happening today. Even if migration today is not mainly triggered by climate change, there are other reasons, but part of it is triggered by climate change. There are other socioeconomic reasons, socio-political reasons, as we know. But there are positive impacts, and indeed, these are to be considered. I mentioned the IPCC. The IPCC is an intergovernmental panel on climate change which studies the phenomenon and publishes a lot of reports. I think it's interesting for you to know that these reports are open access, are freely available. I think they are also licensed under the Creative Commons license, so you can take data from them. They also have chapters focusing on the sea level, sea conditions, sea change. And you can find the website very easily. Just Google IPCC, and then you find the web page and the links to their assessment reports. They are publishing now their number 6 assessment report. The first one, I think it's dated like 2001, something like that. And you find here some examples, graphs, which show the progress of temperature from year 1. From year 1 to year 2020. And you can find also projections. So these graphs show that warming is unprecedented in more than 2,000 years. There is to say that 2,000 years is nothing. So if you look at the history of climate, the history of Earth, you know that it's much longer, 5 million years. So 2,000, it's a long time for us, but it's not a long time for climate. And these data were derived before 1850. You see that up to 1850, you see data are visualized in bold. And this is the instrumental period. Before than that, we reconstructed this data through proxy data, reconstructions, tree rings, limnology, etc. And on the right, you see the graphical representation of what I mentioned to you before. So model simulation without CO2, and model simulation with the human emissions of CO2. And you see that models can simulate recent warming only if anthropogenic forcing is included. Okay, and here you can see the water-related disasters and the damage caused by the costs of water-related disasters in 2022. And what you can see here is that water-related disasters are the most important. So hurricane is okay, it's more atmospheric, but there is a water component. And then drought, floods, floods, storm, drought, floods, hurricane. So you see that most of them are droughts and floods. So the water component of climate change, and floods include coastal flooding, of course. The water component of climate change is indeed important. So the frequency of floods is increased at the global level. Yes, it is increased, but it's still not clear what the drivers are. A slide on uncertainty, which is a topical issue and which is always present when we study natural processes. And uncertainty means limited predictability. So uncertainty just means that our capability to predict is reduced. It may be caused by lack of knowledge, but not only lack of knowledge. There are some phenomena, especially natural phenomena, that even if we knew them perfectly, we wouldn't be able to predict them. And the example is this figure, which displays an effect of chaos. You may know the famous say that a butterfly, the movement of the wing of a butterfly in Japan may cause an hurricane in the United States. This is a say that basically wants to deliver the importance of chaos, unpredictability. There are some natural phenomena that are inherently unpredictable. Potentially it is true, but in practice, I don't think a butterfly can trigger an hurricane. But what it is true is that there are some environmental processes, like atmospheric processes, that if you change the boundary condition of a very limited amount, the outcome at a distance may be tens order of magnitude different. So indeed, potentially it is true. It is true that if you take an atmospheric model and you change the boundary condition just tiny in Japan, you obtain a disaster in the United States. But we are not able to say that in that year a butterfly has moved a wing and has, so potentially it is possible, but we cannot demonstrate it. We cannot provide a demonstration just because the process is unpredictable. So you cannot really observe all the butterflies in Japan and to determine what is happening. But there are several examples in our everyday life where, unfortunately, some tragedies are caused by a very tiny change of some initial or boundary conditions. So if you think about, for instance, car accidents, if you start your travel just 1 second later, maybe that you are not caught into an accident. And there are several cases where some phenomena are unpredictable because they are just random. Okay, and what is science? I think we can avoid to discuss this, and it is this slide means to deliver the importance of testing and validation, and because if you, as an engineer, if you want to trust a model, you have to validate it, you have to test it. And you cannot make a design project by using a model result without any validation. And this is the meaning of this slide. Okay. And then I think this is the last one, which is more conceived for students in climate change, directly climate change related issues. And then let me see. Okay, no, this is just the summary of the test that we perform. I think for today we can close here. Do you have any question while I close my recording?